Okay, we got that going. Then you just got to find a.
Now we've got to find the speaker.
Yeah.
Wait a minute. This is of course not alphabetic here, right? So
Where is Philip? I don't see him here. You want to make him co-host so we can share a screen as well.
yes, that's right. That's right. That's right. But first we have to find him, and I don't know where he went. Again, it was literally, I mean, we stopped talking literally 1 minute before I joined. And he said he had the link.
Okay.
Wait a minute, let me check my email because something is coming in. If he is having, no, it's not him.
Yeah, I'm not seeing him. I mean, it's coming up kind of an alpha order for me, which is useful.
Ray was complaining about being stuck in the waiting room, but
I just had to send the email and I got out.
Oh, there's Philip. There he is.
see him?
Yep. He's in now.
Oh, yes.
Okay, I'll get everybody else in if you want to take care of him.
Okay, Philip, I'll make you co-host, okay? So you can join, you can share your screen if...
I can share my screen.
Yes.
Okay.
Okay, Dean, are we good to go?
I think we are, yeah. We're recording, so.
Okay, great. So it's my great pleasure. Oh, yeah, here's the screen. That's great. Okay, so it's my great pleasure to introduce Professor Philip Phillips as our colloquium speaker today. Philip got his undergraduate degree from Walla Walla College in Washington. It's now called Walla Walla University, as I found out. He got a PhD from UW, and then he postdoced at Berkeley. He spent something like 9 years as a faculty member at MIT, and then he moved to Illinois at Urbana, where he's been ever since. He's a fellow of the American Physical Society and a fellow of the AAAS. And actually, just earlier this year, he was elected a member of the Academy of Arts and Sciences. And so we are very glad to have him today. He will tell us about Noether's second theorem and whether that means there are extra dimensions hidden in cuprate superconductors. Philip.
Thank you very much, Dietrich. It's an honor to give this talk. I asked Dietrich, which talk would you prefer? Noether's second theorem in extra dimensions, or this paper that just came out in Nature Physics? And Dietrich, being the deep person he said, he has said, well, of course, Noether's second theorem. Forget about that Nature Physics fluff. So, okay. I'm going to ask a question. Does Noether's second theorem imply extra dimensions? And I just want to, since I really don't like the fact that there's no audience participation, I'm going to ask the audience to participate. Can you tell me if you've heard of Noether's second theorem? Everyone's heard of the first theorem. Oh, you've heard the second theorem. Okay.
Yeah, Philip, I've heard of it, but I don't remember what it was. So, so it's basically useless.
I mean, she must have proven plenty of theorems, right?
I don't know. Yeah. In the first paper, 2 theorems were proven. But from that first paper, people only remember one of them. Don't ask me why. Okay? Okay. So, this work was done with the help of a math colleague of mine, Gabriele Lanave, and a student, Kritsangapong Limtragul. And it was published in a couple of math journals, Communications of Mathematical Physics and Advances in Theoretical and Mathematical Physics. And for the physicists, there's a review of modern physics on this. Okay, so my talk begins with a question. So I want to just bring this point up. Hinchcliffe has asserted that whenever the title of a paper is a question with a yes, no answer, the answer is always no. This paper demonstrates that Hinchcliffe's assertion is false, but only if it is true. So that's the general background. I know you're not supposed to talk, begin a colloquium with a question, but I did. So that's the disclaimer. Now, what would be the signature of extra dimensions? I'm going to go way back and ask the question, does this have anything to do with electromagnetism? So these are the well-established Maxwell equations, relationships between E and B, and currents. But we know that any formulation of these equations in this way is redundant. It's redundant because E and B are related fundamentally. Faraday proved that. And so the bottom line is that the most fundamental quantity is A, the vector potential. And from that, you can define something that is, from which you can write down all of the equations very succinctly. And it's F equals dA, the field strength. This is the complete exterior derivative. Now, this redundancy in electromagnetism tells you about asymmetry. And it also tells you about a conserved quantity. So let me start with that, since I need to say what the first theorem of Noether's is before I get to the second theorem. So the first theorem tells you about symmetries, continuous symmetries, having to do with any sort of gauge field. It doesn't necessarily have to be gauge field, but it's just any kind of continuous symmetry, which can be represented in a simple differential form. And E and M, as you well know, is invariant under this transformation. And Q is the charge. This equation, innocent equation, tells you something very profound. Any field, if you redefine it with this in the exponent, you don't change anything about your field theory. And since this is in the exponent, Q lambda has to have dimension 0. If Q lambda has dimension 0, this means that QA has to have the dimension of this derivative. So this invariance law tells you what the dimensions of Q times A are. It has to have dimension 1. And that is a sacrosanct thing. Now I'm going to set the charge equal to 1, and I'm going to treat A to have dimension 1, but every statement I make is really a statement about the product of the charge times the vector potential. That's the quantity that has dimension 1. Now the fact that this has dimension 1, this tells you that in the action, the action always has this combination of J times A. This quantity has to have dimension 0, and hence J has to have dimension D minus 1. So the fact that A has dimension 1, you can read off the dimension of the current. And this all follows because of Noether's first theorem. Okay, now the first theorem, this invariance principle tells you there is a conserved quantity. And it comes about by simply applying this to this part of the action. You know that if this is in the action and you undergo this transformation, you will generate a term which looks like this, but you don't want that term in your action. So you flip the derivative on here and voila, you get Noether's first theorem that everyone knows. This symmetry relationship manifests itself in a conserved quantity. And that's what everyone knows. Okay. Now, what I want to ask is, are there any exceptions to this?
Why would there be an exception?
Okay, so I want to review the Pipard problem. The Pipard problem was noticed back in the 50s, maybe before then. And what Pipard noticed is that the penetration depth inside a superconductor depends on the mean free path, which means that something fundamental about superconductivity is not just specified by any of the fundamental constants. You have to tell, you have to provide the information about the scattering with impurities.
Philip, just make sure I know what you're talking about here. You're talking about the mean free path of electrons,
Yeah.
and this is as measured in the normal state.
Yeah. No. It's okay. So it's the mean free path if you have impurities present.
Mm-hmm.
Okay. So
I'm wondering how you measure that.
okay.
No,
So let me tell you how he inferred this.
Mhm.
What he did is he simply sprinkled impurities onto a superconductor, and what he found is the penetration depth changed.
Hmm.
And if the penetration depth follows from the London equation, which has no information other than fundamental constants C, the mass, and the electric charge, that equation is clearly wrong. So then he went and said, well, given this concentration of impurities, what's the electron mean free path? So yeah, you're right. It is within the normal state that he inferred what the mean free path was.
Mm-hmm.
Okay. And then what he did is he said, look, it means that J in a superconductor is no longer equal to some number times A. It's much more complicated than that, because this relationship, which is an empirical observation, is not explained by the London equation.
Philip, why couldn't I just say that you can make it fit the London equation if you let lambda depend on the mean free path?
Lambda from the London equation has nothing like that. There is no quick fix to make lambda mean free path dependent.
But I mean, it depends on the parameters in the Landau theory, right? If you go back to Landau theory.
Yeah, but Landau theory doesn't have anything like that.
I don't know. I mean, another point of view is that in Landau theory, all the phenomenological parameters in that depend on everything. We know they depend on temperature, so why couldn't they also depend
So
on...
if you simply just use, the basic Maxwell equations, and you want to do something phenomenological like Landau theory, you will not derive anything that fits this.
Okay, we'll probably have a bit of time after the talk, so we can revisit that when we are done.
So let me show you what London came up with. What Pipard came up with. Pipard said, this explains what's going on, where this quantity right here depends on the mean free path. This is how complicated you needed to have a relationship between the current and the gauge field to actually explain what's going on. He actually said you need a non-local relationship between J and A. Now people might have forgotten about this, but this is the first example of non-local electromagnetism. Okay, so there's a general way of thinking about this equation. It's not that J is just determined by A at a point. It's this non-local equation here. Okay, so one can think about this as if you just take the derivative of the matter Lagrange with respect to A, the current is now determined by some non-local kernel times A. And that for Pipard, that had a particular form, which explained the impurity dependence or the mean free path dependence of the penetration depth. Okay, now what's interesting about this equation is that whatever the dimension of this quantity is, it affects the dimension of the current. Now I've just, so which means that J has an anomalous dimension. Now the standard result is this. Okay, now if we know anything at all, we know that conserved currents can't have anomalous dimensions. So that's where I want to begin. If you introduce anomalous dimensions for conserved currents, how is this possible? And does this tell you about extra dimensions? Okay, so to get this anomalous dimension, you needed to have broken U1 symmetry. Now, are there other examples of currents with anomalous dimensions that don't involve breaking of U1 symmetry? And if it does not, what is the underlying electricity and magnetism? And this is the question I ask: is symmetry breaking necessary? Okay, so that's the setup. Now, where might this be seen? This might be seen in things we don't understand. One of the things we don't understand is physics of strong coupling. And in my primary field of solid state physics, the paradigmatic problem of strong coupling is electrons in the cuprate superconductors. And the basic definition of something that is at strong coupling is that the independent particle picture breaks down. Collective phenomena is at play. So the major unsolved problem is the metallic state that you have in these systems before you get superconductivity is very strange. And hence, it isn't the standard theory of metals that you use to apply that you use then to obtain a theory for superconductivity. You need something much more fundamental than that. Okay. So the key problem is, how do you go from a strange metal to superconductivity? Okay, now, where is the strange metal? So here's a phase diagram of the cuprates. And here's the strange metal, and here's the superconducting state. Now I've put two numbers, infinity and 0. These are the number of theories that have been constructed in these regimes. And as you see, there's no theory of the strange metal, because it's very strange. It's very easy to come up with theories for superconductivity, but a theory that starts with the strange metal and ends up with superconductivity is very hard. And part of the reason is there's no order that's going on here. Okay. So let me tell you what the strange metal is. Now, to do that, I have to tell you what a real metal is. This you should know from all of the work of Dietrich. So metals are things, as we noted in the answer of John's question, in which electrons scatter off of the atoms or impurities, and this leads to momentum relaxation. So here's the equation for the momentum relaxation. And the Drude model, it gives you this form for the conductivity. And if you let the scattering time go to 0, the real part of sigma goes off to infinity. Okay, and there's a basic restriction in this classical sort of the scattering picture. The mean free path, if you have electrons, which are the charge carriers, can't be smaller than the separation between the atoms. Which means there's a minimum value you can get for the resistivity. Okay, so the standard theory of metals, the resistivity scales is T squared. You have the Wiedemann-Franz law, and the optical conductivity goes as 1 over omega squared. Now, the only thing I want you to note from this is that these two exponents are the same. Okay. Just 1 second, I need to let the dog out or he's going to make it impossible for me to give the talk. Sorry. Come here, Charlie. Okay, these two numbers are the same. Okay?
Philip, you had a question from the audience. What is T?
But T is temperature. Sorry, the resistivity scale is temperature squared. And omega is the frequency. So if you measure the AC conductivity, it should go as 1 over omega squared, and this should go as T squared.
So just I mean, since previously you talked mean-free path and so on, so this is now the temperature dependence due to the electron-electron interaction.
Yeah.
And so, sorry, I'm a little puzzled. The optical conductivity going like 1 over omega squared, that seems to say that it's infinite when frequency goes to 0. But I thought its infinite frequency limit was 1 over rho.
This is the value at large values of omega.
Okay.
So this is the asymptotic relationship so that you satisfy the continuity equation. Otherwise, you would violate it.
Mm-hmm. Okay.
Okay.
But this is so this is large omega.
Yeah.
And the resistivity here is small omega. If I want to think about it that way.
Yes,
I mean,
yes.
This is the DC response.
Right.
When you say AC, you mean far AC. Very high.
Yeah.
Okay, great. Thank you.
Okay. So these two things are the same. So if something is strange, these two things will not be the same. Okay, so now you see what is strange about, here are the experimental facts. The resistivity is a linear function of temperature. In the intermediate range of frequency, it's not going as 1 over omega squared. It's going as 1 over omega to the minus 2/3, which means that exponent, this one, are not the same. And you have a violation of the Wiedemann-Franz law. This ratio is temperature dependent. Okay, so what you have to do is come up with the theory of that before you explain superconductivity.
Sorry, Philip, so what happens, of course, is as you lower the temperature, you go into the superconducting dome, and so you don't really know what the strange metal would do if you could follow it to low temperature.
Right. But you know that you are starting off with something that is not the standard theory of metals.
Yeah.
Okay, and that's all I care about. I don't care that it's not it might not be a T equals 0 state of matter. We know that we cannot assume Fermi liquid theory at the very beginning.
Okay.
And hence the problem is an odd one. Okay, so why is the problem hard? Here's why the problem is hard. We have a problem in which we have a range of power laws. Anytime you see power laws, that's a sign, oh, you might do some critical phenomena, okay? So the key thing in critical phenomena is you introduce a single parameter to introduce how you're going to scale the various parts of the system. And with quantum systems, you have to have a time scale also that is diverging. And let's say that's diverging with an exponent with the standard correlation length, but with an exponent z. So time and space are scaling differently. So if you just divide your system up into this and you apply this scaling to the free energy, and you simply ask, how is this quantity, which is going to tell you about all of the transport properties, how does this thing scale? You end up with a series of laws. And what you want in the cuprates is that you want this number to be 1, and you want this number to be minus 2/3. Now, it doesn't take a genius to see that this is the negative of this. So it's impossible for these numbers to be 1 and minus 2/3. So that's why the problem is hard. The standard sort of scaling that you would do to the singular part of the free energy can never give you these two different numbers. And hence, if that doesn't work, you have to introduce some extra parameter into the system, some other length scale, which is associated with criticality to make any headway into this problem. Precisely what that is the big mystery. Okay.
How about having two different z's?
Okay. Let me So let's treat these two problems as separate, okay? Here's why that won't work, okay? This is 2 minus d over z. D is 3 dimensions. D is equal to 3, which means that you would need z to be negative.
Ah, okay. Okay.
Okay? Okay. Z has to be bigger than 1. So it violates causality.
Okay.
So even if you were just trying to explain this using single parameter scaling, you can't do it. I mean, if you stuck 2 here, you end up with nothing. If you stuck 1, well, the cuprates clearly aren't one-dimensional.
And Philip, just to comment, the same problem applies to sigma, right?
Yeah, absolutely. Yeah.
But with a negative
right.
power, you
Yeah.
would need to have a negative z. And
Yeah. So either of those, you run into the problem. So these scaling laws we derived, 12 years ago to show that criticality just won't work. And those have stood the test of time. And that's why I got into string theory, because of this result. I was looking for something else. Okay, so none of this works. It was a surprise when I looked at the archive one day and I read this paper. It said everything can be explained. Oh, sorry. Before I get to that, let me just tell you why T-linear resistivity is strange in the cuprates. Now, this is the line associated with the mean free path being greater than A. This is the line, and above this, the mean free path is less than A. Okay, now, anytime the resistivity exceeds this point, you're violating what's called the Mott-Ioffe-Regel limit. And these are called bad metals. The fact that the slope is not changing from the part where we understand to this part is telling you that there's no change in the charge carriers when you go from below to above this line. So violating the Mott-Ioffe-Regel limit isn't changing anything fundamental about the charge carriers. Okay? So if it isn't, it's telling you that electrons aren't the charge carriers here and they aren't the charge carriers here. Because electrons can't scatter for L smaller than A. Okay, so electrons aren't the charge carriers. What are the charge carriers? Okay, so is some new gauge principle operative? So let me just ask a more basic question. If the electrons aren't the charge carriers, does anything local carry the charge? Now, if whatever is local is carrying the charge, if there's something else that's carrying the charge other than the electrons and it's local, it would seem as if it's still quantized in some units of E. That, this quantity is still quantized. And we know that A dot dl should be a quantized quantity, HC over E. Okay, so if yes, then this thing is still true. But then if it's just multiples of electrons which are carrying the charge, the electron's still carrying the charge. So it doesn't seem like this is really possible. The only possibility is that nothing local is carrying the charge, which means whatever the charge is, it's scale dependent. And if it is, then this quantity is not quantized. A dot dl is not equal to some number. Okay, now if A dot dl is not some number, then you've really screwed up a lot of things, okay? Because Noether has told us you can't mess with A. A has dimension 1, and if it does, A dot dl is a number. But the question I want to ask is, did she really say you can't mess with A? Okay? Well, now I get to the punchline. Hartnell and Karsh, like 7 years ago, said that, in fact, one can explain T-linear resistivity, the fact that the Hall angle scales like this violation of the Wiedemann-Franz law, and we also showed he can do the mid-infrared omega squared, omega to the minus 2/3 behavior. all of the properties of the strange metal can be explained if you make one assumption, namely that the gauge field, the vector potential, does not have dimension 1. It in fact has dimension 1 minus phi. And phi is not a small number, it's minus 2/3, which means that the current will also have an anomalous dimension. The E field will also have this anomalous dimension, and the B field will be 2 minus phi. Now, let's just look at the last one right here. B is 2 minus phi. There's a reason why A has to have dimension 1, because you take, the curl of A to get B, which means B has to have dimension 2. Well, there's a fundamental reason why that is. The flux is the area times B. Now, if B doesn't have dimension 2, then this is no longer the flux. If this is no longer the flux, this statement here is hugely problematic. And that's why you can't mess with A. Okay? So if this is true, it's requiring some new form of electromagnetism. It's requiring strange electromagnetism. So what I want to get at is, how do you understand this statement? Is any of this, and if this is true, then it's telling you A dot dl is not quantized, which may be the answer to the question of how do you understand the strange metal? Okay, so how is this possible, if at all? Okay, so let's just start with some very general considerations. If A doesn't have dimension 1, and by this I mean Q times A doesn't have dimension 1, there are any number of ways of changing the dimension of A, just introduce weird dimensions for Q, then A can, that's not what I'm talking about. It's QA has dimension 1, okay? So if A doesn't have dimension 1, then this gauge invariant principle is no longer true. So your electromagnetism is not invariant under this statement. Okay, so there's a new gauge principle.
Philip, I just want to ask you something here. Are you trying to say that Maxwell's equations are just wrong? Or are you trying to say that something weird happens in this complicated condensed matter system that makes electromagnetism, when you integrate out the condensed matter degrees of freedom in there, behave differently? Which of those two?
I'm trying to tell you that even in vacuum, there are another set of Maxwell equations. I'm trying to tell you that both statements are true.
And presumably somehow you're going to be able to respect the correspondence principle that all the experiments we've done to confirm Maxwell's equations are somehow still right?
Yeah, absolutely.
Okay.
I hope to do that before my time is up.
Okay, great.
So I've laid down the gauntlet for myself, okay? Okay, which is something I like doing. I don't stay away from controversy. Okay, so, right. Okay, now here's a hint as to what might be going on. This equation that we love, that we teach in field theory, this is the conservation law. The important point is that this conservation law is ambiguous. If I can come up with an operator, a differential operator that I can stick between this and this, that commutes with this, I will have effectively changed the dimension of the current. Now remember, this conservation law came from a gauge transformation. Okay? So what this says is then this would be the new dimension of the current. The current would have an anomalous dimension. But since this came from the gauge symmetry, it's no longer the case that A is going to A plus partial mu lambda. Y hat is involved. Okay? Okay. So what this says is that perhaps now we should try to look at where gauge transformations really come from and see if there was anything that was left out And that is the essence of Noether's second theorem. And this right here is a precursor as to what Noether was actually thinking about. Okay, so where do gauge transformations come from? Gauge transformations come by just looking at the energy defined in terms of the field strength. Okay, now let's just look at this in Fourier space. It's just this quantity right here, where this is just the kernel for, is just a propagator for light. Okay, A is just the Fourier, A of K is just the Fourier transform of A, and here we go. Okay, sorry, I need to let the dog back in. Okay, so where do gauge transformations come from? Well, they come from the zero eigenvectors of this equation. Okay, they just come from just looking at what you multiply this matrix by, so you end up with zero, because that determines the degeneracy condition. Okay, and this statement here that this is equal to zero is just the statement that K is an eigenvector, which is just partial nu. And hence the standard transformation, A is this plus partial mu lambda. So that's where the standard gauge transformations come from. They look, you simply get them by looking at the zero eigenvectors of this quantity. Okay, but if this is a zero eigenvector equation, I can multiply that by anything. And if I multiply it by F, I have a new zero eigenvector. But there are rules, which means this is a generator of the gauge symmetry. So it has to be the case that F has to be rotationally invariant. It can't change the fact that A is a one form. And it has to be that F and K commute, otherwise this wouldn't be a real equation. There's only one solution that satisfies all three of these constraints. F has to be a function of K squared. And if it's function of K squared, delta is the Laplacian. The most general thing is that this is the Laplacian to a power gamma. And hence there's a whole class of electromagnetisms in vacuum in which A transforms in this way. And that is my point.
From what you've said, does it have to be a power of the
Yeah, in fact, it could be some it could be some funky function, you know, e, you know, an exponential of this. The simplest case is that it's just this fractional Laplacian to the gamma.
Okay.
Okay, and the cases I'm going to show you for the dilettante actions I will consider in, you know, ADS space, this is the result which comes out.
Philip, the thing, it seems to me, I mean, I'm gonna have to see where you go with this, but it seems to me that by putting in anything but gamma equals 0, you're going to get, say, the Coulomb law is going to change from 1 over r squared to 1 over r to some power that's related to gamma. Experimentally, we know that's not the case to extremely great accuracy. So I don't see how a theory like this can possibly be consistent just with the standard garden variety experiments on electromagnetism that were done in the 18th and 19th century.
Okay, so you know that Gauss's law is really dependent on the fact that you have 1 over r squared.
Right.
Okay. Okay, and and the reason why you pick areas is that that's the same thing as the area. Okay, and if you were to change that, you would get something else.
Right. And
okay?
Experimentally, we don't get something else. Experimentally, we do indeed get 1 over r squared.
Okay, could you please hold off on your question until the end?
Okay.
Because there's absolutely nothing wrong with what I just told you. The zero eigenvectors of M are larger than just the one we choose for this universe. Okay? So if there is nothing mathematically wrong with them, the electromagnetism that that we seem to be comfortable with is not the only possibility.
No, but it's the one that seems to be realized in our universe.
It is not the one that seems to be operative in the strange metal if in fact you're arguing for A to have an anomalous dimension.
Right, but it does seem to be the one that's operative in vacuum.
I would argue that that's not necessarily the case.
Okay, I'm gonna have to see.
Okay.
Let's debate that.
Okay.
Let's debate that afterwards.
Okay. No, this could all be debated. Okay. Okay. Good. So, right. So this is the new gauge transformation. And so what kind of electromagnetism has such gauge transformations? Okay. As John has pointed out, it's some weird sort of electromagnetism. Okay. So here's the claim. If you go and ask the question, say you have an extra dimension. This is the radial dimension right here, and this is a geometry which is hyperbolically anti de Sitter here at the boundary. This is a black hole. This extra dimension is telling you about the running of the RG coupling, as you all know from ADS CFT correspondence. The point is that if in fact you solve for your action involves this funny kind of electromagnetism in which you have this extra field here, which is scaling with the strength of which is scaling as you go along this direction. The claim is the boundary theory of such bulk theories has an A which doesn't have dimension 1. Okay, so the boundary theory corresponds to something which looks really strange. Okay. Now, the thing that is sort of strange about this is that the claim is that the ADS, the radial direction in ADS is the renormalization group direction. Well, if this is coming about from just running RG and looking at what's going on at the boundary, then you have sort of a funny situation in which renormalization is giving rise to an anomalous dimension for the current. And how is that possible? Because no amount of RG can change the dimension of the current. Okay? So to solve this conundrum, what I want to do is construct the boundary theory explicitly and see what is this funny theory that has this funky scaling of A and an anomalous dimension for the current. Okay, so this is what the action looks like. So it's not the standard electromagnetism. It's one which lives in a higher dimension, and it has this extra coupling here, y to the A, and multiplied by the field strength. Okay, now the equations of motion for this look like this. So at any slice in y, the standard transformations are satisfied, but at the boundary, where y is equal to 0, you have no information about what the gauge theory looks like, which means you have to go and construct the theory explicitly at y equals 0. Okay, now to do that, I want to appeal to a certain theorem. Let's say I'm looking at a function g, and this function depends on two variables, x and y. And let's say that this function g satisfies this differential equation. Delta sub x is the Laplace with respect to x. This is single derivative with respect to y, two derivative with respect to y. And I have this as my Dirichlet boundary condition. Okay? Okay. Now, these two people proved the following theorem. But if I have this seemingly elliptic differential equation, I can rewrite it like this. This equation takes on a very interesting form if I were to eliminate this coordinate. In other words, I ask the question, what is the extension of this differential equation to the boundary? What does it look like? It looks like the Laplacian raised to a fractional power acting on the information at the boundary. And this power is related to this number that you had here, 1 minus a over 2. Okay? So here we have a standard differential equation. And x can be any number of coordinates. Y is just one particular coordinate. I eliminate this equation, and I obtain something which is completely non-local at the boundary. Okay, now what does this have to do with our problem? Let's take a closer look at what this theorem says. It says that if we start with something like this, at the boundary, we end up with something which has the fractional Laplacian. But this is just a scalar field. What do our equations of motion look like? Our equations of motion look like this, where this now is a 1 form. It's not a 0 form, as in a scalar field. These two things look very similar. And hence you would think then that the same sort of fractional construction should still be valid. Okay? These are similar equations. In fact, you can prove this. That at the boundary, the equations of motion don't look anything like the standard ones. Okay? And you can do that explicitly. So in the bulk, you have these equations of motion. Rho is now the difference between the horizon and where you are. Now, if you are, and here's the general result, if A is negative, then in fact, rho is small here. I mean, this quantity is now small here, and hence you'll be getting out the UV information. And this quantity will go to the fractional box operator on the tangential components of the gauge field. And if A is positive, the near horizon region is your, will be the equivalent to the low energy information in your system. And the boundary information will correspond to the near horizon, which means both the UV and IR are described by this fractional Maxwell equation. Okay, so if you start with something really funky in the bulk, either boundary, either the UV or the IR will have very weird equations. And the symmetry relationship for the, that your theory will transform under now will be given by this. Okay, so we have fractional Maxwell equations at the boundary. The current is now related to the fractional box operator operating on A. And as a result, this action is now non-local. And this is what F looks like. It's no longer the standard thing. It looks like this. Now, here is the answer to this question. If holography is RG, then how can it lead to anomalous dimensions? Here's how. There was already an anomalous dimension in F, and hence A already had an anomalous dimension the moment you define your electromagnetism to be this. Because if this is the form of your electromagnetism, then A has to have dimension 1 minus A over 2 to compensate for this. Since it already had this funky dimension, when you run the RG, it's not as if the RG is getting the anomalous dimension for you. It's the fact that you started with a theory in which you didn't have the traditional definition of A. Okay. So this is not really an anomalous dimension. It's just that your theory didn't have the standard definition of what A was. And neither could the boundary. So here's the answer. If you notice this ambiguity in the original formulation of electromagnetism, that namely that this quantity is equal to 0, if in fact this is, then the box operator raised to a power is the thing which you can introduce. This effectively changes the dimension of the current, and here is the new current. Here is the new dimension of the current. You can change it to have any arbitrary dimension you want. And that's one of the things that's come out of the gauge gravity duality, is that currents can have any dimension you want. Because if you just look at the correspondence, you care about the boundary theory. And if you construct what the action is explicitly, you'll see it's one of these funky things. Now, the immediate thing that you should think about is, what do the Ward identities look like? Okay, because that's essentially the question John was asking. So here's the photon propagator. Now, what do the Ward identities tell you? They tell you about a certain vanishing of something, a certain conservation law. Well, if you just multiply by this momentum, and you just do these sums, this quantity will be equal to 0. Okay, that's a standard Ward identity. But the Ward identities are ambiguous, because this side is non-zero. This thing, you're saying this thing is equal to 0 if you contract these indices. Okay, well, it's also equal to 0 if I multiply by this. Well, multiplying by this is equivalent to putting the box operator, the fractional Laplacian there, and you haven't changed any truth about the Ward identities. So this ambiguity about the 0 eigenvectors manifests itself at the level of the Ward identities. Okay, which means now, and this is an inherent ambiguity in electricity and magnetism. So from the family of 0 eigenvectors, the most fundamental conservation law in the universe is this. It's not the one in which you have gamma equaling 1. Okay. Now, how is this related to Noether's second theorem? On some level, Noether actually knew this. Because that's why in the paper that we know and love, which I don't think anyone has read, in the second half of her paper, what she does is she said, look, these gauge transformations I've been considering are not the most general. I could actually generate any number of conservation laws and auxiliary conditions on the current by just including all of the higher order derivatives of this of some matrix. Okay, the simplest one is just this. So what she did is she realized she was playing a game. That if in fact you go and include all of these higher order things, what these do is they simply add constraints on the current. Well, but if you only include integer derivatives here, all you're getting is just higher order integer derivatives of something which is already 0. And hence there's no new information here. And that's why the second theorem, the basic statement of the second theorem is, the class of gauge transformations is bigger than just this first derivative. So the actual statement about the second theorem is that there's something wrong with the first theorem. There's special conditions under which you get that very specialized form. What we have done is consider the case in which, rather than just keeping these integer derivatives, you have fractional Laplacians. And when you do that, your theory now has a much larger symmetry group. Okay, so Noether actually knew this. This is what she was worried about, and that's why she formulated the second theorem. But the form of electromagnetism changes fundamentally. Now, in the context of string theory, this has been noticed now. Noether's second theorem is making a comeback. And in this very nice paper by Avery and Schwab, they said that, look, you can go and involve any higher order derivative you want, and it changes the form of the gauge transformation, although the authors know of no physically interesting examples. Okay, The strange metal is one case in which the actual electromagnetism, if this is true, is an example of these fractional terms that Noether sort of telegraphed are actually relevant. Okay, now what about experiments? Okay, now let's get back to the original problem that all of this poses. The magnetic flux, if B doesn't have dimension 2, this quantity is no longer a pure number. If it's not a pure number, how do you think about the magnetic flux? Okay, so here's how you think about the magnetic flux. You have to invent, yeah, because this thing should be dimensionless, and it's not dimensionless. Okay? It's not, and in fact, if you look at the dimension, this thing is something large, okay? Okay, so here's what you do. You have to act as if you were working with a system that had the standard electromagnetism. So you have to sort of cook up something that has a connection which actually has the correct dimension. And this is the question that you have to ask, okay? So this is just the inverse of what you did to get this funky electromagnetism. Okay, now, whatever A is, there should be a sort of winding that you should impose on either this fictitious A, which is not what's really describing the material, but it's the one that we know and love, and it's related to this one in a certain way, and the actual physical one, which has this funny anomalous dimension. Now, the thing that you can prove is the following. If you look at the winding of this around a closed loop, either this quantity or this quantity can be quantized, but both of them can't be quantized at the same time. In other words, the relationship between this and this is some number here, which is not an integer of the flux. If it's not an integer of the flux, then what this is telling you is that what you mean by the charge is ambiguous. So what this is telling, what Noether's second theorem is really telling you is that there's an obstruction theorem to quantizing charge. Because if the current has an arbitrary dimension, the charge also has an arbitrary unit associated with it. Okay. So this means charge is really ill-defined. Okay, because whatever you mean, you can define one of these two gauge fields, and depending on which, the choice of which one you want to quantize is really up to you. If you were speaking Italian, you would say it's a piacere. Okay, so now you can test this with the following. If in fact pi r squared B should be the, say you have a sample and you thread it with a flux, the flux should be pi r squared B. So this red thing is the whole. But if in fact the electromagnetism that's operative in this strange metal is non-local, then it's not just going to be pi r squared B. It's going to be something that depends on the outer radius. That's going to be the total flux in the system. So the answer to John's question is yes. The strange metal is strange, and you can tell how strange it is from this function right here. This thing depends on the outer radius and the inner radius. So if I'm right, if you go and do this experiment, you should find that there's a large correction. The flux is no longer given by this. There's this large correction on the outer radius. And it's impossible to explain that, as John has sort of boxed himself into a corner here, unless you invoke weird electromagnetism. So that's the answer. Okay, if the strange metal is strange because the charge isn't quantized, and which is follows from A not having dimension 1, then this Aharonov-Bohm effect is going to show that in fact the charge depends on the scale. Okay, so if the strange metal is strange because A doesn't have dimension 1, then what God said is really this. And fractional, the universe that all of the experiments that we've done, the people have done so far, seem to be in one in which gamma is equal to 1, okay? That's fine. But, that's not the only case. We've shown, Noether was absolutely obsessed about this, which is why she has 2 theorems. I don't know why the reason why the second theorem isn't so well known is that there's no new content if you simply stick with integer derivatives. There is if you look at fractional cases, and then you're making new fundamental statements. Okay, so omega is still equal to ck, so the theory is still causal. The Pipard kernel is just one example of this, and in which J does not have dimension 1, J doesn't have dimension d minus 1, A doesn't have dimension 1, and so fractional electromagnetism and superconductivity are related via the Pipard kernel, and Pipard was actually the first person to formulate fractional electromagnetism. We sort of continued it onto a different level, but that's what I just told you about. Okay, so that's really what I had to tell you.
Okay, well, let's unmute and thank our speaker. And I think we have time for more questions.
So there was a question in the chat. I don't know if you want to convey that, Dietrich, or.
Wait a minute. Is there okay? Here's a question in the chat. Is there an analogy here to composite fermions in the fractional quantum Hall effect?
No, those are definitely quantized. It's just a different. It's just what I'm arguing for is that if in fact the charge depends on the outer radius, there is no well-defined charge. So it depends on the size of the loop that you draw around the sample, which is not the case. So here's the interesting thing. If you look at electrons in the lowest Landau level, you've integrated out a bunch of stuff, okay? Now, in that case, the theory you end up with, let's just say that when you know what you're doing, you end up with something that's completely local. If you don't, you end up with the wrong answer. Although initially you might think you're going to end up with something crazy, but you don't. So things all work out for the fractional quantum Hall effect. Okay, John, do you still have a question?
I'm trying to unmute John, but I can't. But let me ask a corollary to. It's very hard to mute John.
That's odd. He's quite vocal in general, so.
Okay, don't know. But let me ask a variation of that question. So why is it that all that stuff is happening only in this particular material? I mean, what you were talking about sounded so much more general, right?
Yeah, it is. Yeah. So
everywhere. Why doesn't it?
Yeah, that's right. In fact, what I would say is that these are the most general Maxwell equations. Okay.
But Philip, we know that those equations with gamma not equal to 0.
No, it's not gamma equal to 0. It's gamma equal to 1.
Right. We know that those equations with gamma equals to 1 describe all the experiments on electromagnetism done before high temperature superconductors were discovered.
Well, I would beg to differ with that. The Pipard kernel is telling you that that is not true.
Okay. Let me qualify that statement. If we ignore experiments on superconductivity, all other experiments on electromagnetism are described by these equations with gamma equals 1.
Right.
That's a lot of experiments. That's
Yeah.
every generator that's ever operated in the world. That's every point charge for which we've ever measured a 1/r² force.
Right.
That's far more experiments than all the experiments on superconductivity put together. They all say gamma equals 1.
So what are you trying to tell me?
I'm
Because
trying to tell you
of
that
that, I should
must have
ignore the fact that the Picard kernel doesn't work?
I'm saying this.
What is
I'm
your
saying
point?
choice. You're
I've
telling
given
me, I'm
you-
not so convinced of this,
I-
but you're telling me that the purport kernel not working says that gamma has to not be equal to 1. I'm telling you
Yeah.
1,000 times as many experiments that tell you that gamma is equal to 1.
Fine, but those are not of the kind that are analyzing what Picard was interested in.
Actually, we have a related question from Dave Soper, who says, so what happens in vacuum? Is in vacuum at least gamma equal to 1?
Okay, so what I've shown you is that in general, this statement is actually true even if you're in vacuum. It's just that we've got
all these experiments that that's not true. We know that's not true. This equation right here. I'm sorry.
Yeah, right. Okay, so but what I'm trying to
will give you a force law that's not 1/r². We know the force law is 1/r². We just know that. It's every experiment shows
John,
that.
hold your horses. I'm just telling you, there is nothing in electromagnetism which allows you to write down anything more than what I have written down.
And how about in vacuum? Let's
Even in vacuum, because where does all of this come from? It came from the fact that the zero eigenvectors of that matrix M are bigger than just K nu. And that is Noether's second theorem. So just get used to it. That's what we have gotten used to, the fact that, you know, we can simplify things. But if you look at the zero eigenvectors of that matrix, it's bigger than just that one point, than just the momentum. And if it's bigger than that, then you have to be honest and just acknowledge the fact that this is the most general theory that you can write down. Now, why is it everything we've seen so far is just 1? So I would say that's the interesting question. There had to be something that happened somewhere to make us observe gamma equals 1.
Okay.
I don't know what that is.
Okay, we have a few more questions here. So one is from Eric Corbin. Is there any hope for actually measuring this effect in the strange metal? And what exactly is it that's so strange about the strange metal that makes this happen?
Okay, so I would say the following: there is hope. An experiment is a feasible experiment is of the following kind. You take a cuprate, you punch holes in it, you know the area, and you measure the magnetoresistance. And the question you're asking now is the periodicity of the magnetoresistance Hc over E? If it's not Hc over E, and it's of the kind that I just described, then you've proven that in this material, there is this funky electromagnetism. Okay, now I would say that electromagnetism was always a phenomenological theory. Okay, it just happened to be it's a fit. Okay, so if you're seeing that, as in superconductivity, the electromagnetism requires a fundamentally new relationship between J and A. If you have a strongly correlated system, what's carrying the charge might not have any particle interpretation. And if it doesn't have a particle interpretation, then there's no reason to assume that the way the light interacts with that is going to be the same as if, you know, you had your garden variety piece of copper.
Well, sure, because you've integrated out all this extremely complicated stuff, and you'll wind up with a system that's very, very far from vacuum, right? Or
Yeah.
from copper. Okay.
Yeah.
Okay. And a related question in the chat is, what is it that determines gamma for a particular situation, for a particular physical?
Okay. That is the real question. Well, actually, that's one of the questions. Okay. Look, okay, that I don't know. Okay, that I really don't know. I mean, what you really are asking is, what is the, you know, as Dietrich has pointed out, you've integrated stuff out. You have all of this, the strongly coupled soup. You don't really know what the charge carriers are. Your model here is really, you know, to derive what gamma is extremely difficult. You need to know what all the interactions were. But I can tell you how you can get rid of gamma. If gamma is different from 1, it's telling you that you're looking at a projection from a higher dimension. So if gamma is different from 1, then it's telling you the universe is really a hologram. Okay?
Including vacuum?
Including the vacuum. Yeah, that's right. That's right. So, yeah, I mean, I think we're, yeah, that's right. That's right.
Okay.
Because what I've shown is that these fractional equations all become ordinary differential equations in a higher dimension.
Okay. Another thing, so Spencer Chang was saying, so is it that in a strange metal we need an effective theory that makes the gamma not equal to 1, right? I mean, that's a very very integrated out stuff.
Yeah.
And Agu is asking, with respect to John's issue, so if gamma is not equal to 1, do you still have the 1 over r squared law?
No.
Okay. Why isn't that a problem?
Okay, so this is the interesting point, okay? The reason why you never want gamma, why it's uncomfortable having gamma not equal to 1 is that the theory is inherently non-local, which means that, you know, if you wiggle something over here, you're affecting, you know, the field lines will go out of, you know, if you, let's just say there's a material in which gamma is not equal to 1. Well, that's in contact with the vacuum. So what happens in the vacuum should still be gamma equal 1. So then what's the interface? How does that match up? Okay. I don't know what the answer is to that question.
So if gamma is not 1 inside of cuprate superconductors because of solid state effects, I'm not too unhappy. But if it's not 1 in the vacuum, then I know that we have experiments from distance scales of 10 to the minus 15 meters up to distance scales of hundreds of parsecs. And then I'm most unhappy.
Okay. So all I'm saying is I don't know how to prove that gamma is equal to 1 in the vacuum from, you know, first principles. Okay. These are the
experiment. You can tell, right? Because
but that's not a proof. That's
well,
just an experiment.
We plan use experiment.
I mean, in other words, if these are the most general Maxwell equations, I have to appeal to something else to say that gamma has a certain value. If you want to say that Coulomb's law allows me to eliminate anything other than gamma equals 1, fine. But that is not the question you asked me. Can I theoretically set the value of gamma? And I would have to say no.
Okay. So gamma is a parameter in your theory.
Yeah. I mean, gamma is telling you about the multiplicity of the 0 eigenvectors of the photon propagator, as it were. Okay? It's telling you about this thing that Noether pointed out in her second theorem. Because she was well aware that there was nothing unique about stopping the gauge transformation at the lowest order that she did. That everything about gauge theories depended on what you meant by the gauge transformation. And if that's true, then we should just face up to that.
Okay. So it's getting somewhat late, so I would say let's thank our speaker again. And
Thank you.
let people give a chance. Let give people a chance to leave if they want. If you want to stick around and discuss gamma a bit more, then just stick around. I'll keep the session open for now.
Yeah, I have time to talk about, this is my favorite topic, okay, because it's shocking, right? I mean, it's very odd that no one really understood Noether's second theorem until now. Not that I really understand it. I understand the implications of it.
Okay, so did Emmy Noether actually realize the implications for electromagnetism when she formulated?
Well, remember, she was a mathematician.
Yeah, but she knew a bit about physics.
She did, but okay. So I don't know. She knew that she was dealing with continuous symmetries, and continuous symmetries formulable in terms of a differential constraint always lead to conservation laws.
Mm-hmm.
But she knew that that statement was not profound. At least it's not as profound as we think it is. Because the equation of motion that you end up with has an inherent ambiguity. And that's why she came up with the second theorem.
Okay.
Okay? So I don't know if she knew that this would affect electromagnetism. I mean, but you know, the thing of it is, if you look at what she did say this leads to a hierarchy of currents, which leads to a hierarchy of charges. Okay? And that much she did say.
Okay. Okay. Okay.
Okay?
Okay.
I mean, you know, she's probably the physicist I'd like to meet the most if I possibly could, and ask her, did you really understand what was going on with electromagnetism?
And so Pipard's kernel.
Yes.
You say that's a bona fide example of this.
Yeah.
So what is the gamma in his that follows from his kernel?
Okay, you can work it out. It's in a paper. It's in the review of modern physics paper that we have.
Okay.
Okay.
So this has, then you're saying this has nothing to do with high TC. I mean, this stuff is at work in a perfectly ordinary BCS superconductor.
Yeah, and it makes sense, right? I mean, if there's any phenomenon that is non-local, it's superconductivity.
Yeah. That's right. That's
okay.
Right. Yes.
So, and you know, we tend to think that electromagnetism was just given to us. No, it's the interaction of light with matter. So if it's light with matter, well, if you break U1, there's no telling that you know what ultimately what other stuff you have to give up.
Okay.
Okay, and so I think Pipard was onto something very fundamental. Were you aware of the Pipard kernel?
Yes, but I had no idea that it implies extra dimensions. I mean, it's in Tinkam's book, right?
Yeah, right. It's in Tinkam's book, so I'm not just making this stuff up. I mean, if anything is well accepted, it has to be well accepted to have been in Tinkam's book. I mean, it's the Pipard kernel. So there you go. Now, the reason why you might not have made that connection is that there's a paper by Weinberg called Superconductivity for Particular Theorists. And it's an absolutely brilliant paper. And it talks about all of the consequences of breaking U1 down to Z2. It talks about the Pipard kernel, because this is the relationship that he ends up using to go and deduce what is the form of the electromagnetic energy from this kernel that's responsible for the expulsion of the magnetic field. Okay.
Okay.
So it's a very general paper, and it tells you how to think about superconductivity just from U1 down to Z2. And in fact, that's the paper that makes it clear that in general, J can have an arbitrary dimension because it will depend on this quantity C.
Is that how he actually put it?
That's how we put it. But actually, he didn't take that step. He has everything set up, but he didn't realize that this means that the dimension of J is arbitrary.
Okay, that was Progress Theoretical Physics Supplement 1986.
Yes, there you go.
Okay, here it is. Okay,
There it is.
okay, okay. Okay, I was not aware of that. Okay.
Yeah, it's a nice hybrid paper so you can talk to high energy people about superconductivity. And so.
But the particular theorists he has in mind.
Well, okay, so this paper was written, I think, in the context of Nambu's birthday.
Yes.
I forgot which one. And so he had in mind people like him who are particle theorists.
Okay. 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 Okay.
So it's a pun, actually, okay?
I see. Okay. Oh, okay. Okay.
Yeah.
Okay. Okay. Yeah, so coming back to the vacuum question. So are you aware of any indications that there's something weird about electromagnetism in vacuum as opposed to strange metals?
No, I'm not aware of anything.
Okay. Okay.
Right.
Okay.
Right. I'm not aware of anything. And I think this degeneracy is telling us that we live in a very fine-tuned universe.
Where gamma is equal to 1.
Where gamma is equal to 1. Yeah, and if there are exceptions, it shouldn't surprise us because this is the most general way of thinking about it. You know, your question, could you have raised this to a power? Is this some exponential of something?
Could we make it a weird function? Yeah.
Yeah, you could have made it a weird function, okay? It's just that when you look at dilettante theories of the kind that were constructed in string theory, it's always this asymptotic form of the dilettante, which is this algebraic function to some power.
Okay.
Okay? And that's where all of this comes from.
Okay, well, very interesting. Thank you, Phillips. So it gives us.
Well, there are other people who might have other questions. Someone else has to ask a question besides Dietrich.
I had a question. So besides the strange metal, could a system that exhibit fractional vortices could be a possible system where Noether's second theorem manifests?
Possibly.
These bilayered Josephson junction arrays that, like, there have been a few examples where you can fractionalize a vortex into integer or like half, 1/2 fractions.
Okay.
I was wondering if those could be possible systems where.
Okay, now here's the thing. To explain that, you don't need A to have any dimension other than 1.
Okay.
Okay? So fractional charge alone does not. Okay, so let me go back to my, how do I, oh, I've used this thing here. Let me stop share, do this, and go back to my original, when I laid down the gauntlet here. Okay, right here. Let me share the screen again. Okay, so you see, in those cases, although it might be fractional, it's still point-like. In other words, the low energy theory is ultimately something with, integer, in which you just need to look at the momentum has a well-defined power, the action is a well-defined power series expansion. Okay. Okay. Right. So I would say in those cases, this avenue is still true. Something local is still carrying the current. Okay. So what is weird about the strange metal is that we've been beating our heads against the wall for 30 years or so trying to figure out what's going on. So I think the problem is you can't describe it using a local theory, and whatever is carrying the current doesn't have any particle interpretation.
So by no particle interpretation, do you mean just like no single particle interpretation?
Yes.
Does that extend to like composite particles?
Yes. Yes. Composite particles are still particles because they're still poles in something.
Yeah.
Okay. So I would say unparticles. Okay. In other words, the propagator is the forward momentum to some power. Okay. When you have stuff like that, then all hell breaks loose.
All right. Thank you.
Okay.
Okay, anything else?
Oh, sorry. I know this is not relevant to your talk, but may we see Charlie? Is that?
Charlie is the miracle dog. Charlie is so old. It's amazing. He's alive. I will show you Charlie. I think, yeah, here's Charlie. Charlie, smile, you're on candid camera.
Sorry, is that a diaper on him?
No, this is just the bowl of food. Okay, so.
Oh, okay, sorry, I heard old dog, so.
Okay, so here's the thing. Charlie has.
Don't mind me.
And plus, he looks very large, right? Yeah, he's bloated, so his days are numbered. He has congestive heart failure, or he's filled up with all of this fluid.
Oh.
And so we are trying to figure out exactly what to do because I have to lift him outside, and so anyway, this has been going on for a couple of years, and I'm still amazed every time I wake up that Charlie's still around.
What is he?
He is 14.
That's
So
all.
he is a soft-coated Wheaten Terrier. I'm not a dog person. I'll tell you how I got the dog since you asked the question. Okay, I tend to be honest. The neighbor across the street, they had the dog. Her husband died. She has scoliosis, can't take care of the dog. And Charlie basically adopted me. And so that's how I became a dog person.
I see. Okay.
Otherwise, I would not have a dog, okay? Because I think it's hugely irrational and, you know, but anyway, there you go. But I take care of Charlie and I can't quite figure out, you know, what the humane thing is to do. So if you have any suggestions, maybe we should talk about that right now rather than anomalous dimensions for the current, which John Toner seemed to be really upset with. Is John still there?
I
He
don't.
had office hours, like around 5. So
Yeah, office hours, okay.
Sorry.
Okay.
Don't take it personally, though. He's normally the most entertaining professor at Colloquium.
Well, no, I knew that. I gave a live talk at Oregon many years ago.
That was a long time ago. Yes.
Yeah, I was not anywhere near any of this stuff, and I remember he asked lots of questions.
He's laughing, I think, because he saw me out here. Because I'm talking about dogs.
Hello.
Okay. Cool. Well, thanks a lot, Philip. I think
Thank you, Dietrich. This was definitely the correct topic to talk about. I mean, when you tell, when you tell people that, you know, we live in a fine-tuned universe and there's generally an obstruction to charge quantization, they pay attention.
Yeah, when you told me about this stuff, I looked at it and said, "Hey, I want to hear about this." So
Okay.
okay, so I think we should all go and think some more about gamma not being equal to 1.
Yes. Yes.
And if we can come up with more questions, then we'll email you.
Yeah, absolutely, absolutely. I respond to email about fractional electromagnetism. Is my favorite topic, so there you go.
Okay. Okay. Cool. So thanks again.
Bye-bye.
Bye.
Okay.
And we can't even take you out to dinner, which is too bad.
Well, I guess in Oregon, you'd probably just go running.
Well, yeah, but it's kind of foggy and gray today. We just go out to excuse me, to a nice restaurant, but some other time.
Absolutely. Absolutely.
Once the vaccine comes around, we'll do that. Okay. Yeah. Bye.
Okay. Bye-bye.